Alright, let's talk solving for 0. And before we do that, actually let's talk about this time period we just ended up in. 0 to 1600. This is where all the juicy bits of history of numbers really comes into play. So let's start late 1500s, alright? And this is very well known to be a time period of Descartes. Descartes. That's how you spell it. But Descartes, Rene Descartes, he developed the coordinate system. It's where you take 1 point. You could even take negative points, but either way. 2, let's say 3. Well, guess what? You can reference this point in respect to this point by calling this one 0, 0, the center, and this one 2, because that's this one, and 3, that's this one. They're both called ordinates. Well, technically this had another Latin name, but now today we call them the coordinates because they're both known as an ordinate working together basically. So 2, that would be co. Alright, so that's Descartes. But interesting enough, we studied quadratics, which you usually imagine drawn on these coordinate systems. Well, they studied them even before Descartes intimated. In fact, let's go back to the 1400s. This is about the era when we truly understood the quadratic. And a quadratic is ax squared plus bx plus c, where a, b, and c can be anything. Pretty much anything. Let's not be crazy here. Alright, so solving this for 0 is an integral part of solving a quadratic. Because a quadratic might exist. You might be able to plug in a number and get a result, but here, let's talk. Why is it called a quadratic? Just really fast. Well, quad, think 4. What's a 4-sided shape? Oh, a square or rectangle. Well, rectangles are the ticket. If you have a side of ax and a side of x, the area of this whole thing is ax squared. And then if you have a rectangle of, let's break it up into parts, of x and 2, let's say x was 2, and let's say 3x plus 3, sure, why not? 3x times x is 3x squared. 3x times 2 is 6x. X times 3 is 3x. 2 times 3 is 6. Let's add them all together. 3x squared plus 6 plus 3x is 9x plus a 6. Alright, this is what we'd call a quadratic. And so studying when that's equal to 0, which is basically, it's literally saying when is this whole area right here equal to 0. And it's also accepting that negative areas would cancel out, whatever. Finding out when this equal to 0 was huge during this time period. And you can ask many reasons why. I could probably make up a ton of problems to investigate it. But why do that? I think you get it. It's solving anything in this form for 0. And now, today, we have a formula for that. And we slowly developed this over the time, and it became well known. And it's not super hard to prove. It's not a crazy jump to say that it's true. So there's our beautiful formula. Check that out. It'd be plus or minus square root of all this stuff, b squared minus 4ac, all divided by 2a, and those letters pertain to these letters. And so every quadratic could now be solved using this. Now, we didn't have a problem. This actually didn't innovate the, well, it kind of innovated the imaginary and complex numbers, but it didn't really do anything. Because here's the thing. What's the square root of a negative number? We understand the square root of 4, per se, is 2. Or it could also be negative 2, because negative 2 squared is 4, but whatever. 2 or negative 2, sure, either one works. But what's the square root of negative 4? Guess what? All we say is does not exist. We just said it didn't exist. And we were happy about that because it makes sense. even graphically it makes sense. I think this is kind of before its time, but we still can use some logic about it. Hey, this is when the inside of the square is positive, because squares that are positive simplify nicely. This is also a circumstance. Alright, these are circumstances with 2 zeros. Now guess what? We could make a circumstance with only 1 zero. And guess what? When that happens, it's when we don't have a positive or negative case, because this guy is 0. And plus or minus 0 is the same as adding nothing to the equation. And so this is the case where we get only situations where it touches the axis once, when we only get 0 one time. So, yep, that was acceptable. And then you get those cases when we don't touch it whatsoever, when there's no point in space in which this equation would equal 0. See how it never touches? Therefore, and that only happened when the inside of the square root was negative. So it only made sense that this does not exist when the inside of a square is negative. And both support each other. This support itself because it's like, oh yeah, it doesn't exist. That makes sense. That's a way you could draw a parabola so it does not touch this axis. And this one also made sense. There's no number that we know of at the moment that squares to be a negative number. And so it just made too much sense that, yeah, the quadratics didn't bring up anything new. All it brought up was these new ways of working with algebra. And which was pretty amazing, actually. Working with algebra changed the world. And we still use algebra in basically every field for a reason. But now you're thinking, alright, so then Imaginarius never came into play. No! Let's move on here. Let's move to the mid-1500s. This is an era of the Renaissance, and one of the things that the Renaissance did was they brought up things from classic Greek times. The Western world, at least, did. So things that basic Greeks did, sculptures and theater and all that stuff, came back into play during the Renaissance, these 1500s. And so let's think. One thing that the Greeks loved was mathematics. It was at the heart of things, and it's all logic. And so this was a time period when we really started bringing back classic mathematics. And so there were actually competitions in the streets of Italy where two people would be competing against each other to solve a situation like this. 4-0. That way, one classic way to represent the quadratic to solve for 0, just a quick indicator to help you understand this guy a little bit, is if you can represent this as 2x's multiplying. I don't know what 2x is multiplying, but this is a method for just solving a regular quadratic. Well, you know that this will equal 0 if either one of these is 0. They might be 0 at the same time. They might be 0 at different times. Different x values, that is. But solving this for 0 is usually a lot easier, because usually this situation inside of here is just a simple linear equation, which are really easy to solve because there's only 1 0, nothing special. So we know solving both of these for 0 was great. That it really made all this equation solving nice, because even though it looks complicated, you know that you could take either one by itself and set it equal to 0, and then you'd still be solving for 0, if that made any sense. Yeah. So we tried the same thing for these guys, cubics. That's what these were called. And it went downhill. They're just too complex, and even though it's just 4 different coefficients to work with, this is not something easy to solve. And by the way, you might see them more often represented like this. Ax to the 3 plus bx squared plus cx. And then all of this is times, well, equals d. And so you could actually this would be negative d in this case, but usually they didn't like negative numbers, so they'd keep everything as positive as it can by adding it to the other side. So it's not negative anymore. So if you had -5 as your d, well, now adding -5 to this, I would put it like this. So you'd have this whole equation equals 5, and so you're solving for 5. Whatever. That's the 0, and you can solve, and zeros are special because you can solve for any value, not just 0. It just so happens that's one special value. But anyway, cubics. Let's stay on topic here. Why are these so bad? Well, turns out they were so bad that it's almost like I'm telling a joke. They were so bad that we only could solve them in these circumstances. And this is called the depressed cubic because it makes you depressed. No, that's also another joke. No. But they are called depressed cubics because you're moving a term. You're depressing it. You're subtracting something from it. So these depressed cubics were a lot easier to solve, and so what we did was we rearranged it, did some substituting in X. It got complicated, and people were very creative about it. And then we broke it down into a quadratic form, like this. These are different letters altogether. Ignore the fact that I'm reusing the same letters here. Well, guess what? These are easy to solve because we already have the quadratic formula. So it was very genius. It was about transforming things, and so you could solve them. So that was a huge thing during the 1500s. So there's actual instances. Two famous guys, Cardano and Tartaglia, and I think there might have been one other. And what they do is they basically have a duel. They would sit down. I don't know where they'd be, but maybe it'd be in the middle of the street, and they're both given a cubic to solve. Let's say 5x cubed plus 3. It's not like I'm going to solve this in front of you. And they were both told to solve it. So both had their own secret methods, their secret things to do to solve this. And then the first one to solve it correctly, that is, with an x that works, would win. And by the way, they'd probably be more proposed like 5x cubed plus 2x. Something like that. They might be more proposed like that. But these two gentlemen had their own Cardano and Tartaglia, and there were others, but these were the two big guys during this time period, Cardano and Tartaglia. And they had their own methods for solving it, and they kept them secret as they could be. These were trade secrets that they only told very few people. In fact, I think, if I remember it right, Tartaglia actually told Cardano his secret formula, and he used it in the wild, but whatever. Either way, important thing to get out of this. They developed their own methods, and then Cardano was the one to develop the cubic formula. And he didn't even understand it, to be honest. Because here's the problem. There's very easy values in the cubic formula that solves any cubic like this. After all of these years of development in the mid-1500s, Cardano put together this formula that's basically a combination of everyone's efforts during this time period to break down this problem so it's easier to solve. So break down this so it's a depressed cubic, and break down this so it's a quadratic, and break down this so it's just the quadratic formula. And they're very hideous formulas. I wish I showed you. But anyway, Cardano over here put this all together in one giant formula. But the formula had a bit of a problem. So let's first think about what this problem might be. So we already know it's going to include square roots because of the quadratic formula. So let's just carry out the square root kind of case. So let's draw some cubics. Cubics are going to look like this, where they have 3 zeros. They're going to look like this, where they have 1 0. They're going to look like this, where they have 2 zeros that are technically 3 zeros because this one counts twice. Whatever. You can get complicated with it. Whatever. And there's no cases where it's no zeros without some problem arising. Like it not being a cubic in the first place. Like the A term being 0. That would, of course, make it so it's possible to have only 0 zeros. But this is the problem. You're always going to get a 0. Alright? And we noticed that the square of a negative does happen. It does happen. It's a possible case. And it's when this doesn't touch the axis. But this guy will always touch the axis. And so you can expect with some number out there that you're going to get a square root of a negative number. And so Cardano really doubted his formula because people kept bringing up, hey, this can't be right. You're getting square roots of negatives. How can that give you a real result? And what it told us is that you actually have to go, it's kind of like a portal. You know, you're kind of going through to this alternate universe for a second, just so you can get to, you're going through this cubic formula, which deals in all these square roots of negatives, and cubic formula, and it deals with all this crazy stuff, but you start with the real idea, this real formula, all real numbers, all of these are real numbers, and you solve it so you get a real number out. But the only way that works is dealing with square roots of negatives and such, even if they cancel out in the long run. So this is bizarre. It's truly bizarre. There's no way to get rid of the square roots of negatives, and so someone out there had to accept that a square root of a negative existed. And so that gets us to our next video.